decades. But the output of RAS signaling is an inherently systems-level behavior that comes from all of those activities working together to drive RAS through its cycle. And it's not immediately obvious what's going to happen to this effector assembly process when you attach it to an actively cycling network like you see here. And I think it's something really worth considering because the components that move RAS through its cycle exist in a variety of different network configurations across different cells, which may indicate that different setups of these same components can be used to produce a variety of different outputs. And so I wanted to develop a systems-level reconstitution of RAS signaling that could capture some of these processes. And our strategy was to prepare RAS-coded beads and place them in a solution of signaling components, and then monitor the actual assembly of effectors onto the bead surface using fluorescence microscopy. And this is what the raw data from these types of assays looks like. There's a RAS-coded bead, and if you supply activating GEF and GTP in the system, then you see effector assembly build on the bead. And using the system, you can turn up the assembly process by adding increasing amounts of GEF, or you can turn up the disassembly process by adding increasing amounts of GAP. But most importantly, you can combine assembly and disassembly reactions together to create an actively cycling network. And I just want to emphasize that within these actively cycling networks, a steady state like you see there is actually a high energy non-equilibrium steady state, in which the observed effector output that we see is being maintained by a constant consumption of GTP energy in the system. And these high energy states actually end up being really valuable for us to be able to prepare, because these are precisely the types of states that most strongly distinguish wild-type and diseased alleles of RAS from one another. And to show you what I mean, if we initiate assembly in a low-energy, gap-free context, wild-type and oncogenic alleles of RAS behave almost identically to one another. However, in the context of a high-energy, high-gap context, their behaviors are completely divergent, with wild-type producing a transient response compared to a sustained response by oncogenic RAS. And so why might cells ever operate in these high-energy regimes if a single point mutant can completely short-circuit your intended assembly program? Well, it turns out one of these things these high-energy states can do for cells is they can actually sharpen the discrimination between competing effectors. And so to show you what I mean, if we assemble a signaling network that contains both high-affinity BRAF or lower-affinity CRAF as downstream effectors, and trigger assembly in the absence of GAP, you can see it takes a long time for the cell to be able to discriminate these systems, these effectors from one another. But when GAP is included in the system, we accelerate their discrimination. And so this result motivated us to take advantage of our in vitro system to perform a systematic characterization of the different types of RAS effector assembly behaviors that you could generate by varying each component of the underlying network architecture, which is really something that you can only do with an in vitro system. And this generates a huge number of these assembly curves, which you can then use to develop a quantitative model, as well as an intuitive design manual that reflects how different network configurations can be used to generate different patterns of RAS effector assembly. And I just want to share one result that was surprising from our quantitative model, which was that it shows that it's actually possible to use these GTPase systems to create programmed sequences of effector binding by simply titrating the concentrations and modulating the off rates of your different effectors. And what this means is that cells may be able to exploit these to create distinct early or late phases to their RAS signaling outputs. And so one thing I'd like you to take away from this RAS component of the talk is that when you see a RAS system or a RAS-coded surface, whether it's the beads I'm preparing or the plasma membranes of a cell, you should think about those as versatile platforms that can use the energy of GTPI hydrolysis like a machine to facilitate programmed sequences of molecular assembly. I think ultimately what the cell builds in response to different signals is going to determine the types of decisions it makes. And so I think this is a valuable framework for thinking about RAS signaling. And so from this part of the talk, I hope you'll agree with me that by combining components together and reconstituting higher level networks, it can help us understand and build in vitro systems that can do a variety of interesting control or organizational processes. But at the same time, I think you'll agree with me that we have a long ways to go before you could put some molecules in a tube and get something coming out the other end that displays the complexity of cellular systems. And so with that in mind, I want to tell you what I'm currently up to, which is trying to use the animal-like behaviors of unicellular protozoa to understand how cellular machines could be programmed by simple combinations of signal transduction and mechanics. And so for those of you who aren't familiar with ciliates, these are extraordinary eukaryotic single cells that execute fantastic robot-like behaviors like you're seeing here. And none of these videos are sped up, meaning that these are largely pre-assembled molecular machines that are running at timescales much faster than transcription.